There are many strange phenomena in machine learning. One of them is called overfitting. The key idea with overfitting is that there is more and more data available, and therefore we would feel that the more data we have, the more complex the rules we're going to build are, and therefore we are encouraged to build more and more complex rules, and we hope that the more complex the rules, the better they work. This isn't quite true. To illustrate this, let's take the following data set. You can notice some blue points and some red points. The blue points correspond to the class of objects we're trying to learn about, and the red points correspond to what we may call counterexamples, examples that would not be true. So we are in a typical machine learning setting where we are going to try to learn with 90% of our data points and put to aside a 10% of the data points for later testing. So we decide to learn what is called decision trees. In other words, we are trying to learn boxes or combinations of boxes. So here we have seen how we have tried to learn just one box. So that is the figure to the left. So we can just see one very neat box, which is trying to approximate the blue with comparison to the red. But then we can try and learn more complex boxes, which is a combination of boxes. So of course, if you want to have a box, you've got four sides defining a box, which is why we are calling this a decision tree with four rules. So to the right, you can see a much more complex pattern. So to try and better fit the blue points and separate them from the red points, we have entered a number of boxes. We've done 50 rules to define the boxes. So obviously, if we look at the learning data, the 50 rules will fit better the data than the 4 rules. If I only do 4 rules, there's obviously going to be some red points which are going to be inside the box or some blue points that will be outside the points. These are, of course, mistakes. But if I do much more rules, I will be fitting nicely. So this is what my blue line is illustrating. We have been seeing how over time, which means over the number of rules I am applying, we are making an error which is going smaller and smaller. So this sounds like something that is good news, which is reinforcing the idea that the more we learn or the more complex we learn, the better it works. But what happens when we look at the test set? You remember there were 10% of the data points we decided to leave on one side, where we now use these. So these are points that have never been used before to build the hypothesis, and we want to see what happens when we run our boxes on these points. And we obtain the figure which is to the right, which is we can see that at some point the red curve, which is the curve over the test set, starts going up. In other words, we're making more and more mistakes over the unseen data with the rules which are becoming more and more complex. So this is the phenomenon of overfitting. Overfitting means we aim so hard to find rules that adapt to the reality that when a reality that we hadn't seen before appears, we're actually going to make mistakes. Another way to see things is that we are failing to generalize, or the earlier solution with just very simple boxes was generalizing much better than the second solution in which we were building a too complex solution. Now, this phenomenon we have just observed is something that has been known for a long time. William of Ockham, in around 1300, came up with the idea that when we had various explanations to a phenomenon, it was always better to choose the simplest answer. So this is not just common sense, it is not just philosophy, it is also strong mathematics. And in mathematics, you can prove that this philosophy of going for the shortest or the simplest answer is actually well founded. It also corresponds to the idea of compression. In one case, we are trying to find a very nice crispy rule or set of rules to represent the data. In the other, the set of rules we're trying to invent is too complicated and we are doing less compression. Of course, we shouldn't just take this for granted and go for the absolutely simplest. It's just a question of compromise. We need something which is simple and explain well the data, and usually that is a good solution to machine learning. So this phenomenon of overfitting applies to machine learning, but does it apply also to deep learning? Deep learning models can be huge. The GPT-3 learning model was 375 billion parameters. So that was a huge amount of data. Well, actually, in fact, it also applies there. And researchers and practitioners who work on deep learning also have to avoid the overfitting phenomenon.